synchronizing traffic lights in metropolitan areas. As you scale up, the number of intersections becomes a very complex computational task. So the project is really to test the feasibility of quantum algorithms and see what kind of an added value can we bring and reduce traffic congestion.
Traffic congestion isn't just a daily annoyance, it's a multi-billion-dollar drain on the global economy. Can quantum computing solve this problem today? Quantum art is moving beyond theoretical simulations to use quantum algorithms for synchronizing traffic lights and managing flow in metropolitan areas. They're also building a unique trapped ion architecture that performs operations on dozens of qubits at once to drastically improve speed and fidelity. Let's explore the practical hybrid future of quantum classical processing in this episode of the Post-Quantum World. I'm your host, Konstantinos Karagiannis. I lead quantum computing services at Protiviti, where we're helping companies prepare for the benefits and threats of this exploding field. I hope you'll join each episode as we explore the technology and business impacts of this post-quantum era. Our guest today is the co-founder and CEO of Quantum Art, Tal David. Welcome to the show.
Hi, Konstantinos. Glad to be here.
Yeah, I'm excited to have you here today because you guys announced a major real-world project with Ayalon Highways to optimize traffic routing. And, when people think about quantum computing, they're always thinking about, well, what are you going to use it for? Is this just going to be some nerdy thing that exists in the back of some cloud room somewhere? No, actually, there's some real-world use cases. So can you set the stage for us? What was the specific problem you were trying to solve? And what are the limitations of the classical tools that are in use for the same problem?
Sure. So I guess everybody knows traffic, right? We're all standing in it all the time. And actually, there was a report last year from the US that said that tens of billions of dollars are lost because we're spending time sitting in our cars instead of being in our offices and working. And what we did is we bunched up with Ayalon Highways in Israel, where we are located. This is the biggest traffic planning and management company in Israel, which is working together with the Ministry of Transportation for the government here. And we got to an understanding that synchronizing traffic lights in metropolitan areas, as much as it sounds, a simple task, it's quite quickly, as you scale up the number of intersections that you want to synchronize, becomes a very complex computational task. And therefore, we thought, okay, maybe we can look at quantum computing and see if it can bring value for that. So the project is really about to test the feasibility of quantum algorithms in general and quantum art specific architecture and see what kind of an added value can we bring and hopefully be able to provide value and reduce traffic congestion, which I think is something that everybody wants.
So is it a quantum problem because there's a sheer number of variables that's just so huge from all these intersections that it gets out of hand? Is it because you need near real time, or is it some kind of like combination of the two that makes it a quantum problem?
Right. So we separated it into two levels, the planning and the management of traffic. The planning is not real time. You could plan how you build the intersections and what are the control loops that the traffic lights interact with or operate in different times of the day or other considerations like that. So that's not real time at all. And the complexity there comes from, computational load. As you have more and more variables and you need to plan ahead the traffic flow, you need to have more and more computational power, and the combinatorial complexity blows up quite quickly as you go beyond 4 or 5 intersections with traffic light. And then the next level will be really management and seeing how fast can we do this optimization and react in, I wouldn't say real time, but near real time to what's happening on the road. And this will be a second step in our project.
Okay, so first you build the system for the roads that really aren't going to change anytime soon. Like they might change once a year or something, right? Like basically which intersections, whatever. But then you've got to also have this extra level of, it's raining today a lot, or something. Is that the kind of idea? Like you have to be able to respond to that sort of like change?
Well, I would say that in the first level, the roads don't change, but we can improve how we control the timing of all of these intersections working together. And the second thing, maybe it's to react to rain, but I would say more if there is a certain traffic accident that changes the flow in the roads, if there is, I don't know, a tree fallen in some place and we need to react to that, or if you have really, really strong rain, maybe that as well.
So that is near real time then, right? Yeah, because like weather, you could predict tomorrow, you might have to make changes, but a tree falling or an earthquake or something is not really always very predictable.
Yeah.
Yeah, so it has to run. So now, speaking of running, I'm sure listeners are curious, what is this running on that makes it quantum right now?
So at Quantum Art, we're developing and building quantum computers based on trapped ion qubits, full stack, hardware, software, and applications. When we do these use case development studies, we start from pen and pencil and paper, and then go to simulations on classical hardware, and then move to the quantum hardware. And in this project, we'll do the same thing. We start from modeling, understanding the problem, identifying the relevant approaches of how to solve it. Then we go to our simulator or emulator of the quantum system, which is a full quantum emulation of what we have in the lab. We understand what is the expected added value, and then we'll go to our qubits and actually implement them, the algorithms there.
So for now, it's running on full state vector simulation.
Yeah, we have a few levels. Some of it is physical, and then we go to circuit level and get the noise model into that circuit level simulation as well. So it has a few layers that we can play with, yes.
Okay, and you have some results then that you'd like to share about where you are right now with the listeners, like how it runs at this level?
Yeah, so this project was just announced. We're just starting it out, so there's no result just yet. But I can tell you from other use cases that we're doing with other partners and customers that we can show nice results. Maybe before that, we should say that the architecture that Quantum Art is bringing to the table is a little bit different than what other people in the industry are doing. For
Yeah, I was going to
example,
ask you about that, but you could talk about it now
yeah,
for sure. They're not just the
yeah.
trapped ions that everyone else is familiar with and how they
Yeah,
operate.
so first of all, it's trapped ions. That's the best performance modality out there, improvable numbers. But beyond that, in our architecture, we go and use sophisticated tools. For example, instead of doing single and two qubit operations in sequence like what other people are doing in the industry, we go beyond that and do multi-qubit gate operations on dozens of qubits at once. Okay, thereby we're saving a lot of time and a lot of error and so on. So, for example, we have a use case study that we're doing with a partner in Israel now on solving partial differential equations, specifically the wave equation. You could think about a use case of looking at the RF propagation of waves in cellular communication, and we want to solve that in a very large area. So their initial results that we have show a 10x to 100x improvement in the depth of the computation for a given problem size relative to other approaches in quantum computing, and we're quite excited about that. Or a different use case study that we're doing for a year now with a company in California called Blue Qubit is a use case of doing quantum machine learning for image processing. And there also we're showing tens of percent improvement in the reconstruction of images when we load them into the neural network and then in classification tasks as well. What we're doing there is that Blue Qubit are bringing their algorithm and we're translating that into our architecture with multi-qubit gates and so on to improve the performance. So that's just a few of the use cases that we're doing to show the added value from our architecture.
So when you run your simulations or emulations, you're trying to match exactly, like you mentioned with noise, exactly what your physical systems will perform like, right? So you have similar,
Yeah, that's correct.
and because your first one is 50, is it going to be 50 qubits for the montage system?
Right, so the montage system, we already have it working in the lab. We'll launch it in just a few months' time for cloud services with a gradual ramp up in the first part of 2026. We're also in discussion of selling a standalone system of that generation. So this will be a 50 physical qubit system, but with our multi-qubit gate. So already there, we're bringing something that is a little bit beyond what other people are doing in the industry. And if you want, we can talk about the later part of our product roadmap to the future.
Yeah, I'm going to want to get to that. But first, I wanted to try and get a sense of these are physical qubits, obviously not logical ones. So with those performance improvements that you mentioned, do they get you a little farther along the line of doing error correction? Do they make the process easier? How does that look like to establish some kind of ratio from physical to logical?
Yeah, so we're looking at a ratio of about 1 to 10, roughly, and we're looking at different error correcting protocols in order to do that. So in the first system of 50 physical qubits, it will be just a few logical qubits, nothing to write home about. But in the next generation system that we'll have in a couple of years, this will be a 1,000 ion system segmented into 20 cores of, let's say, 50 qubits each, working in parallel to each other. And then the architecture warrants itself quite nicely to do error correcting codes, because the way that we segment the very long ion chain is by using optical tweezers that pinpoint in place a couple of ions here and a couple of ions there. Thereby, these tweezed ions become like barriers, and in between these barriers, we have segments or a few tens of qubits each that perform the multi-qubit operation. So you could imagine that in each of these cores, or each of these segments of a few tens of qubits each, in one multi-qubit gate operation, we can encode logical qubits into the core. So in one code line, essentially, we're moving from the physical realism to the logical realism. And then, in order to connect information between the cores, we do not move qubits around mechanically like qubit shuttling, as you could find in other trapped ion architecture. Rather, we can just use our optics again to change how the optical segmentation occurs. So it's kind of reminiscent of how an FPGA works in electronics, right? You have certain configuration of the hardware, and then you give a command to reconfigure how the hardware is connected inside. So for us, if we have these tweezer beams segmenting the long ion chain, we can just turn these tweezer beams in a microsecond in one configuration and turn them on in a new configuration. Thereby, we can connect hundreds of cross-core links between these cores in a very fast time without moving any qubits around. So if before we said that we are in one step of multi-qubit gates encoding logical qubits into the cores, now in one reconfiguration step, we can do logical operations between logical gates, between logical qubits in our multi-core configuration. So it's quite nice and warrants itself natively.
So it sounds like you're developing your own kind of interconnect, right, for these modules to work together?
Yeah, so usually when people talk about interconnects, they're talking about how to connect different separated systems to one another. For example, if you look at the superconducting guys, they can get to a certain number of qubits in their dilution fridge, and then they need to interconnect different fridges together. For us, we're not connecting or interconnecting separated systems. Rather, we are segmenting optically a very long ion chain, and then we're playing with how this segmentation is configured. So we are connecting information, but it's not in the sense of interconnecting separate systems to one another.
Well, when you mentioned earlier that to get to 1,000, you'll have multiple 50 qubit of these systems. That's what I meant, like connecting those 50 qubit pieces together. It
Yep.
sounds like you've developed your own
Mhm.
way to do that, right?
Right, so we just need to turn off the lasers in one configuration and turn them on in a new configuration. For example, we can move between two scenarios, one that you have a certain segmentation, and the other one is that you have like a shift in the segmentation of half a core. So it looks like a brick wall structure like that. So we can take in each configuration step half of one core and half of another core and form them into a new immediately all-to-all connected core. And this is done on all of the cores at once. So therefore, if we had a 50 qubit core size, we connected instead of shuttling one qubit to one qubit, we're connecting 25 to 25, and we do that on all of the, let's say, 20 cores or so. So you mean you get to hundreds of cross-core connections in one step like that.
Okay. So with that machine, that will be, let's say, 1,000 down to around 100 logical.
Yep.
Is that around 2027 that one's expected?
Yeah, we intend to start selling these systems first for cloud services and then for standalone during 2027, so about 2 years from now.
So that machine should, with that many logical qubits, be able to provide some type of advantage. I would imagine. I mean, you can't simulate that many logical qubits.
Yeah.
Do you have any particular first application that you're targeting, solving, or working on with 100 logical qubits in mind?
Yeah, sure. So as I said before, we're looking at, I would say, two main families of applications. One is solving partial differential equations, which has many applications in communication technology, in aerospace, in automotive, and security. And the other family of applications that we're looking at very seriously is quantum machine learning that we're using for anomaly detection in images, or to what we'll do with Ayalon Highways in optimizing flow patterns in traffic, for example.
Okay,
And
yeah, I
these
was
are,
asking if you had some new one that you can't even touch yet until you till you reach that level. That's what I was curious about. If there was
I
something you
think
would.
I think I think that's enough for now. We'll have a
Yeah.
lot of value to give already at that level, and that's only the beginning, right?
Yeah.
Because our architecture goes way beyond 1,000 qubits as we go along towards the end of the decade. So we have a lot to do for sure.
So all this is like a two-dimensional architecture, right? With the way these ion.
Everything that I've talked about so far is one-dimensional ion chains,
Hmm.
but we have full programmability and we have all-to-all connectivity, so we can make the ions behave as if they are in a two-dimensional array or a three-dimensional array. After the next generation product that we call Perspective in 2027, that will be the point that will go from a one-dimensional chain of ions to two-dimensional arrays, or actually a mesh of rows and columns working together. And because we're not doing shuttling, we can maintain the ion-ion distance as it was in small scale, so just 5 microns or so. And this gives us the ability to have these two-dimensional arrays with very high density. Okay, our first generation of the 2D arrays will be 12,000 qubits in a 10 by 10 millimeter footprint. And at the end of our roadmap, after the turn of the decade, we will extend that up to 1 million qubits in a 50 by 50 millimeters or 2-inch by 2-inch footprint, which is quite dense, I think, if not the most dense QPU out there in any of the architectures.
But it still is pretty wild to think it's just inches, and you have all that horsepower trapped in just inches. That's kind of amazing. So for IonQ to plan out their new roadmap that they hit us with earlier in 2025, they changed things up and they acquired Oxford Ionics, of course, to do their whole electronic gates and improve their speed, and then LightSync to chain all those QPUs together. How does your gate speed performance compare to, let's say, what's projected out with the electronic Oxford Ionics gates?
Yeah, so that's a good question, and both of these companies are doing amazing stuff, and we know them and hold a lot of value to them. The differentiator in quantum art comes to mitigate the shortcomings of speed of operation, connectivity, and the size of the QPUs. So for example, when we're doing a multi-qubit gate, we are essentially, instead of doing all of these 2-qubit operations one after the other, we're doing them in one physical operation, in one go. For example, if we'll have 10 qubits in our multi-qubit gate, it will be equivalent to about 45 2-qubit gates that are done in series, but we're doing them in one go. So we can save up a factor of 40. If we extend that to even 50 qubits in a multi-qubit gate, we can save up a factor of 1,000 in the timing of these gates. So in terms of speed of operation, we think that we can bring a lot of novelty and innovation. And also, as I said before, we're not doing qubit shuttling because of our optical segmentation thing. So we're not wasting the a long time people are spending on moving these qubits around and recooling them. We just don't have that. So in terms of speed of operation, we win by a large factor. And also in terms of the footprint, because the length scale that determines the size of the QPU in our case is just the qubit-qubit separation, which is on the order of 5 microns, and not the length scale that determines the size of the traps that you're moving qubits from one trap to another, we can get to extreme density, and therefore the footprint does not explode. And as I said before, because we're doing this optical reconfiguration and generating in one step in a microsecond hundreds of connections instead of doing one-to-one links, then I think that we're bringing something also new in that respect. So certainly the fidelities that IonQ and now Oxford Ionics has demonstrated is amazing. But I think that the architecture of qubit shuttling has its challenges in speed, in footprint, and in connectivity that we try to bring a mitigation way to handle them.
So instead of sequentially worrying about the timing between the gates, you're doing your multi-qubit gate system and you kind of make up for that then because so much more has been done in that 1 microsecond or whatever.
Right. The reason that gates in ions are relatively slow is that you mediate the interaction between internal energy levels in one qubit to another through motional modes, and that takes a little bit of time. Okay, so the order of 100 microseconds or so does not change, but we managed to squeeze many operations to the same length of time that other people are doing one gate. So that's the thing
Yeah,
here.
yeah, that's what I just said. Yeah, absolutely. Yeah, it makes sense. So you don't have to worry so much about how fast that ultimately is if you got all those done in that, in that amount of time.
Yeah,
You don't have to worry about sequentially going through 10 when you just did the 10 in one swipe,
right.
basically.
We do have stuff to worry about. Okay, it's not easy to do,
Of
but
course. But just
yeah,
that general approach, I understand it. It makes sense.
yeah.
So what are your biggest challenges then now with error correction? Because I think you're going to have to kind of create your own version, right? In some ways.
Well, yes and no. We could use, the surface codes that many people are using, but I think this is kind of a limiting code because you're limited to a surface, and we don't need to be limited to that. So we're looking at other codes like LDPC or the Tesseract code. Some of these codes have, because of their topology, a challenge in scaling up. So we're looking for ones that utilize the best. We're also working with partners on these things. I think that the main challenge going forward is, and that's true for all quantum computing, is stability, stability, stability. We need to have everything really robust and stable in order to maintain the highest level of fidelity. Also, in that respect, we're doing some fun stuff because even before going to multi-qubit gates, we have demonstrated something nice, which is called robust gates in our language. The idea there is that usually when you're doing even two-qubit gates, you need to be exactly right in your working point in terms of the pulse timing, in terms of the laser intensity, in terms of the stability of the trapping field that is holding the ions, and so on and so forth. What we're doing is doing a precursor to the multi-qubit gate ideas, and that is that on top of the standard bichromatic laser drive that we're doing to generate standard Molnar-Sorensen gates, we're sprinkling a little bit of tones of other laser frequencies on top of that, and that uses to cancel out some of the noise sources or the instabilities in the system in order to get a wider envelope of working conditions that are still the same as that desired working condition. So even if we have some instability, let's say 10% in the laser intensity fluctuations, something like that, we still can maintain the best fidelity that we have. So robustifying the gates like that with coherent control techniques is something that is nice because you could do real large scale algorithms, practical algorithms, and not worry about too much about stability. And on top of that, we still try to stabilize everything we can in the system to have the best performance we can.
So on that topic of performance again, to bring it back to the real world application that we started with, how do you see that changing the day-to-day life of a driver in Israel right now when it's running in a simulation mode? How do you see it changing when it's running on 1,000 qubits within 2 years, let's say? How do you see that evolving?
All right, so the simulation stage is just to understand what's the potential and what is the expected added value. We want to understand if quantum will bring any added value. It's not clear that any applications will win from quantum. You don't want to do 2+2 or quantum PowerPoint, probably. So the first thing we'll do in the simulation level is to understand if there is a considerable added value to be had. And then the other question that we want to answer is, okay, if we have a very good added value, what's the quantum computer that we need? Do we need a quantum computer of 20 qubits or 50 qubits or 1,000 qubits? And essentially, when will we have that kind of quantum computer? And then moving to the hardware, according to the answers that we get in the first part, we'll understand if we could bring this value, first of all, in planning or also in near real time. I guess there will be differences there. And secondly, what is the scale that we can do this optimization on? Do we do that only at the around Central Park in New York, or can we do that in all of Manhattan, or can we do that in larger areas, and at what time in our evolution of the quantum computing industry?
And when you're setting up these parameters, one of them has to be access, right? Bottlenecks. One of the challenges for using quantum computing for something like fraud detection is there's only a handful of really good ones, and you want to be running them all the time if you're trying to detect fraud, and that becomes an issue. There's only so much to go around. So have you given thought to what might be required to control access? Like how would you make sure that something could feasibly be accessible in this use case? Like, do they have to access this machine every hour? That kind of thing.
Yeah, so if you're doing planning, you need to do that every once in a while. That's not a problem of access. And the key factors in order to provide that kind of solution is, first of all, to have the most stable systems and higher uptime as you can. And secondly, to have as many systems as you can. So we're starting with one system and we're building other systems as we go along. Another aspect that could be maybe considered is not to go through the cloud, but actually having a standalone system in your facility that you don't need to wait in line with other customers in other applications and so on. But that's a trivial statement, right? In terms of the near real time, I think that the issue there is, first of all, to understand that we need a playbook, right? When we're designing the multi-qubit gates for that particular task, we don't need to do that on the fly all the time. We can have like a menu of the needed multi-qubit gates in our algorithms and then tweak the parameters as we need, which is something much, much faster than that. And also we can use a hybrid operation between quantum and classical working together in order to make sure that only the really necessary parts done on quantum will be done on the quantum side, and the rest will be done on the classical side. So we have classical platform in-house. We're working with our good friends at NVIDIA on how to work best with their GPUs together. We're working with other partners on how the interface between quantum and classical should work together in real life applications. So we're considering that in a very serious way, because as we scale up, even if we'll have 1,000 qubits in a couple of years, we'll still need for the foreseeable future a very strong classical platform to go along with it in order to allocate the resources in an optimal way. So we're very much seriously looking into these matters as well.
Yeah.
And I think that many others also do that. That's not a big secret there.
Yeah, that's a good point. A lot of people forget that most quantum use cases are hybrid. It's some amount of classical, then you give to quantum what quantum does, and then right back to classical again. Even Shor's algorithm is hybrid.
Yeah, for
The
sure.
very first algorithm. Yeah, that's true. So with those hybrid use cases, are you also going to be relying on other NVIDIA technology? For example, do you foresee NVQ-Link coming into play with your systems?
Oh, for sure. So NVQ-Link, as far as we understand, is an evolution from what NVIDIA did previously with quantum machines in the DGX quantum, right? So the idea there is to create a fast link between the GPUs and the control system of the quantum hardware. So they generalized that now, and they can actually do that with any control system. So for sure, one of the things that we're discussing with the NVIDIA team is to progress towards that and combine these things together. It's really important for hybrid. I think it's really important for the faster operating qubit technologies like superconducting qubits. In ions, we have the luxury of being a little bit slow. We take care of that with our multi-qubit gates, as we said before, but the individual frequencies and so on are a little bit more relaxing. So I think it's for us, it's more relevant really for the hybrid operation with classical, and not so much for the actual, gate dynamics that other people are needing that for.
Yeah, I think NVQ-Link's going to come up in just about every company's news over the next few months. I think they're going to find some use for it.
Yeah,
I do hope it improves also just this idea of error correction in general. Like I think there's a chance for it to do something there. So with that said, I hope everyone will check out your site that'll be in the show notes and follow along on the progress of this use case. And I hope you update the world on how it's going, because I do want to see more of this very tangible kind of thing that you can notice by whether you're stuck at lights for an hour or only 40 minutes or whatever it is. So thanks for coming on to share that with us.
yeah. Thank you for having me, Konstantinos. I'd love it.
That does it for this episode. Thanks to Tal David for joining to discuss quantum art. And thank you for listening. If you enjoyed the show, please subscribe to Protivity's The Post-Quantum World, and maybe leave a review to help others find us. Be sure to follow me on all socials at Constant Hacker. That's Constant with a K, Hacker. You'll find links there to what we're doing in quantum computing services at Protivity. You can also DM me questions or suggestions for what you'd like to hear on the show. For more information on our quantum services, check out Protivity.com or follow Protivity Tech on X and LinkedIn. As we do every year, we skip the episode around the holidays. So until the new year, be kind and stay quantum curious.